Welcome back to Gaffy's Grinds. In a previous lesson, we learned how Avogadro discovered the following. He discovered that if you took a container and you filled it with a gas, let's say you filled it with 1 liter of gas, okay? And let's say that that gas was oxygen. That's a gas we've all heard of before, right? So 1 liter of oxygen gas. And let's say that oxygen gas, so there's 1 liter of it, and you counted the particles that were inside the box when it was a 1 liter volume. What you would find is there would be a certain number of particles. Now, this isn't the correct number, but I'm modeling for you here. It doesn't really matter. Let's say we go 1, 2, 3, 4, 5, 6, 7. Let's say there are 7 particles of oxygen gas if we have 1 liter. That's what Avogadro was looking at. And what he discovered was, well, if you took that same volume, 1 liter, of another gas, so this time 1 liter, of another gas, which was, say, carbon dioxide. Now, of course, these are molecules, so there are going to be 3 atoms in each group, right? So let's say 1, 2, 3, 4, 5, 6, 7. Well, what you would find is that there are equal, so it would have 7 carbon dioxide rediscovered, that equal volumes of gases contain equal numbers of particles. We can confirm it again by doing it a third time. Let's say we took 1 liter this time of helium. Helium's another gas. Again, what we would find was, okay, 1 liter of the gas would contain 1, 2, 3, 4, 7 particles, or 7 atoms in this case, of helium. Okay. Now, I should have said, sorry, the oxygen, of course, are diatomic, so they actually are 2 atoms. Okay. So it would be actually 7 molecules, just to be fully correct. Sorry. Yeah. So helium will be single atoms. There will be 7 of them. The other 2 are molecular substances, so they would have 7 molecules. But that's the rule here that Avogadro discovered, right? I'll just recap it for you. Avogadro discovered that equal volumes of gases contain equal numbers of molecules under the same conditions of temperature and pressure. So long as we don't change the pressure, we compare them all at the same pressure. Now, what that also means, though, is that we can reverse that rule. What do I mean by that? Well, we could take 2 gases. Again, let's do, try and think of some more now. Fluorine, chlorine, Cl2, chlorine, and let's do argon. 2 gases, and we put them in a container. And we put in 10 molecules of chlorine. So chlorine, again, is diatomic, 10 molecules. There they are, they're diatoms. So there's 1, 2, 3, 4, 5 molecules, 6 molecules, 7 molecules, 8 molecules, 9 molecules, and 10 molecules. And if we take argon and we put the same number of particles in a container, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 particles of argon, atoms. If we put equal particles of a gas into a container, what we'll find out is that they'll spread out and occupy equal volumes. So let's say that this was 1.5 liters in volume, well then, so would this one be. Has to be 1.5 liters. So we can reverse Avogadro's law. And what this means is that if we take a mole of substance, 2 gases, so say we take 1 mole of a substance, nitrogen, 1 mole of N2, and we put them in a container. Here they are, loaded in here. Now, of course, I can't draw this many, but if we had a mole, we know we have 6.2. And then we took a mole of oxygen. So 1 mole of oxygen, and we put them in a different container. There they are, 1, 2, 3, 4, 5, 6. Remember, a mole is always 6.02 by 10 to the 23. That's how many there are in here. If we take a mole of either of these substances, oxygen or nitrogen, then they have to have the same volumes. That's what Avogadro's law says, right? They have to have the same volume, so long as the conditions of temperature and pressure are the same. Now, it turns out if we measure this at STP, standard temperature and pressure, if we take a mole of these 2 gases, or we could keep going here and do any other gas, if we're taking this many particles of it, exactly Avogadro's number, then they're all going to have the same volume. And it turns out that so long as we measure them at STP, the volume will always be the same. It's 22.4 liters. And what that does is it gives us a fixed relationship in which we can use to calculate. It gives us a ratio table where we can compare moles with liters, moles to liters of a gas, basically. Okay, and the rule is, or the basic relationship is, that there's always 1 mole for every 22.4 liters. That's the relationship. Now, if we do it at room temperature and pressure, this is another thing sometimes we can be asked about at room temperature. Well, room temperature is a little bit higher than standard temperature. Room temperature is about 20 degrees, so 293 Kelvin. It's a bit higher than standard temperature and pressure. That causes the volume to increase, but the volume will be 24 liters in that situation. And again, it doesn't matter which gas it is, it's always the same. If you have a mole of it, if you have 6.02 by 10 to the 23 of any gas particle and it's at room temperature, it will always have a volume of 24 liters, right? So that gives us a second ratio table at STP. Moles to liters, therefore, is going to be, for every 1 mole, we've got 24 liters. So this here is probably 2 things that's worth taking down, okay? Fixed relationships, and these are what we refer to as molar volumes. In other words, the volume of 1 mole. Okay, so the molar volume, the volume of 1 mole, and it works, of course, it only works for gases, okay, because gases are free to spread out and fill up a container. Liquids and solids aren't really. So gases will always fit this many particles, or this many particles will always fit into 22.4 liters if it's at STP, or 24 liters if it's at room temperature, if you've got 1 mole. Right, so let's use these 2 ideas here, or these 2 fixed relationships, to solve some problems. What kind of problems can we be asked here? So let's have a look at an example problem. Okay, so one example problem could be, what is the volume of SO2 gas, so we know it's a gas, at STP? Okay, so in this problem, we're going to use a ratio table, and that ratio table looks like this. Okay, so we want to solve the problem. We want to find out, we want to go from moles to volume to liters. Okay, now again, we usually start by trying to write down our fixed relationship if we have one. In this situation, we do, it's at STP. So the fixed relationship is 1 mole is equal to how many liters? Pause the video and write it down. Okay, you should have said 22.4. Okay, so we'll write that in. 1 mole is 22.4 liters. Okay, but we don't have a mole, we have a quarter of a mole, or 0.25. So we're going to put down here, we're going to go 0.25. Now, how do we go from here down to here? What are we doing on the mole side? On the mole side, we're multiplying by 0.25. What some of you might have seen, you can divide either, you can divide by 4, but I prefer to always multiply. And if we're doing that on the left here, if we're changing the relationship on the left, if we're times them by 0.25, but we want to do the same proportionally on the right here. So multiply by 0.25, and you should get, put that in your calculator, you should get 5.6. So the volume of that gas, a quarter of a mole instead of a full mole, is 5.6. And again, logically, that should make sense. We've got only a quarter of the amount of particles, so we should only quarter of the volume, and that's logical, right? So that's how you do something like that. So I'm going to get you guys to pause the video, and when I write this one out, you do the following one. You do this one. You do, what is the volume of 0.3 moles of CH4 gas at, okay, pause the video and doing that one now. Okay, so what you should have done is, and again, you should only be watching this video if you've got it done. Okay, what you should have done is, again, we're going from moles to liters. So it's only a single conversion that we've got going on here. And we know that the fixed relationship is at STP. So the fixed relationship is 1 mole is 22.4 liters. Okay, and this time we're going to 0.3 moles of the gas. So of course here, what we're doing is times it by 0.3. So on the other side, proportionally, we've got to do the same thing, 0.72 liters. So 0.3 moles has a volume of 6.72 liters. Now, I didn't do that in the previous one. That's bad practice. I should have done that up there. I always advise you to do a little concluding sentence like that. I think it's a good idea. And that is kind of how we'd expect you to be able to do that. Right, on to the next bit. It can, of course, get a little bit harder because you can be given a more complicated problem where you've got more than one conversion. But you know how to do all the previous ones. So we'll just combine this on top of what we know already. So they were asked what of STP. So hopefully, again, you can spot the problem here that we have been given the quantity in grams this time instead of moles. Now I'm just going to see if I can very quickly find my mind map or my roadmap here. Here it is. There we go. Okay, and our roadmap, you see here, we want to go to volume of a gas, that's STP, but we're starting with mole mass, right? We're starting with grams. And as you can see, I told you before, there's no direct link here. You cannot go directly across. If you look at the connection, you must go through moles, right? You must go to moles and then to volume. Okay, so we've got mass to moles or grams to moles, and then moles to volume, moles to liters. Okay, so two conversions. Again, nothing new there. We've done this before. We've just got now a new way of solving these problems. Forgive me now while I find this left off. Here we go. Okay, so if you think you can do this, let's go ahead and pause the video and see, can you do the conversions by yourself? So pause the video if you're ready and you think you can go ahead and do this, do it now. Okay, if you weren't able to do it, I'm going to help you lay it out. First of all, go from grams and find the moles of the substance. That's conversion 1. And then in conversion 2, we're going to go from moles and we're going to find liters. Now you should be ready, if you weren't already before, to pause the video and do it. If you really still couldn't do it, I'd be a little bit concerned if you weren't able to have a go at this stage. If not, then you need to go back to the previous sections where we learned how to go from grams to moles. Okay, so grams to moles, of course, is going to be our first connection. And of course, that depends on the substance. For 1 mole, we want to find out how many grams there are. Okay, so this involves calculating the molar mass, right? So the substance is SO2. Okay, so that's going to be 32 for the S plus 16 for the oxygen times 2, because there's 2 of them. And that's going to give us 64, right? So 64 grams in 1 mole, but we have 3.2 grams. 3.2 grams. So what we want to do is we want to proportionally change 6.4 to 3.2. So how do we do that? Again, if you know now and you recognize it, pause the video and finish this up. Okay, of course, it's hard to see the relationship from 64 to 3.2. So what we do instead is we go to 1. Okay, so 64 down to 1 means dividing it by 64. And then 1 to 3.2 means times it by 3.2. So we're going to do the same on this side now. So divide by 64 and then times by 3.2. So get your calculator out, and I'm going to do that with you now. And again, try and stay ahead of me, 64. So we got 1 divided by 64 and then times by 3.2. I'm getting that's 0.05 moles. So there are 0.05 moles in 3.2 grams of SO2. Now we're ready to take that number, that moles number, and put it in the second table. Just reconfirming that it is at STP, which means that for 1 mole, there are 22.4 liters, not 24, right? Okay, so we're talking about this number now, 0.05. So this is the same as what we did in the previous questions, times by 0.05, times by 0.05, and we're going to get 22.4 times by 0.05, and I'm getting 1.12 liters. Okay, so just to conclude, there are in 3.2 grams of SO2. Okay, so that's concluding that problem. Now, of course, they can get even more complex where they need multiple steps, multiple conversions, but they're all things that we've done before. The difficulty in the exam questions at higher level leaving cert is that they require you to put together a number of these steps. They get more complex, right? And you have to work your way through them, thinking your way through, okay, what do I go to? What do I convert to? And again, always a good idea to keep this map in mind. This map is really useful to have as a big picture in your mind. Sorry, I've kind of drawn all over it now at the moment. But I mean, this is, to be honest, this is something I would even practice. I don't think it's any harm to practice drawing that map out, right? Because that is your roadmap to solving all the different types of problems, right? Now, practice on that is going to be, so there you can see there's the relationships that we looked at, that we do that now, okay? And then to answer the rest of those problems should give you lots of good practice here, okay? Just a little tip that RT obviously stands for room temperature and STP stands for standard temperature and pressure. 24 if it's at room temperature, 22.4 if it's at standard temperature and pressure. Right, folks, so you've got lots of problems to practice there. So you're working on this next set of questions just down below the molar volume section there. In my booklet here, it's 170 to 185. If you're using a newer version of this booklet, the numbers might be different, but the questions are the same. And that's it, guys. I'll see you in class the next day we go through them, okay?